Well, it is 2 p.m. in Chicago, which means it is time for Vamos. It's my distinct pleasure to introduce Andrew Houck, today's Vamos speaker. Andrew was an undergrad at Princeton before moving to Harvard for his PhD, where he worked up the street, actually at MIT and Ike Chuang's group. After that, he moved to Yale for his postdoc, working with Rob Shulkoff, pioneering some of the very first circuit QED experiments. There are actually a ton of things that I admire about Andrew and his science, but the feature that I most try to emulate myself is his ability to cross-pollinate between intellectually disparate areas. He truly originated this idea of exploring many-body lattice physics in circuit quantum electrodynamics, or making matter out of light in some sense, and has spent years developing these ideas. In parallel, he's advancing state-of-the-art qubit technologies along a ton of fronts, from material science questions all the way to harnessing ideas in topological protection to engineer better qubits. He is extraordinarily creative, and I'm really looking forward to Andrew showing us what he's got. Let me just say, I would like to invite all of you to pose your questions either through the Zoom interface or through the YouTube chat. There will be 2 breaks during the talk, during which we will address the questions. So with that, I will hand it off to Andrew.
Thanks, John, and thanks for Vamos panel for inviting me here. It's something I've been looking forward to for a while. So I'm going to talk about our lab's efforts over the last decade, really, to engineer synthetic quantum materials with superconducting circuits and really to make matter out of light. Over the last decade, there have been a number of things that we've made that have been fun and exciting, from this dimer to these 1D lattices with dissipative phase transitions to multi-mode cavities and photonic bandgap crystals and all kinds of things. And one of the great joys about superconducting circuits is that you can kind of make whatever you want. What I'm going to focus on today are sort of 2 things. First, I want to sort of focus on these set of experiments that are not grayed out, which is really making weird lattices. And it's this real question of, if you can make anything you want, right? If we can just draw circuits and make them, what are actually interesting lattices to make? And in some sense, that's almost too much flexibility. The other thing we're going to look at today is actually turning on interactions, and not just sort of strong interactions between our photons, but these unusually strong, ultra strong interactions. So what happens when our atoms get these gigantic dipole moments? And we're going to look at how that interplays with the openness of the quantum system and with the many different modes of the system. Okay. So to start, I know this is an AMO audience who might not be as familiar with the circuit, so we're going to sort of build up from the most basic building block. And in circuits, if you want something with a known frequency, the most basic building block is an LC circuit. It has a frequency given by the inductance and capacitance. If you're a quantum mechanics person, you say this is a harmonic oscillator. You can label 0, 1, and 2 microwave photons. You can write a Hamiltonian for some number of harmonic oscillators, say Dagger A's, and life is good. There's another trick we can play. If we really want to get fancy, we can replace our inductor with a Josephson junction, which is more or less just a nonlinear inductor. And if that's the case, it's the same kind of story, but our potential softens a little bit. It's a cosine potential rather than a pure parabolic potential. And so what happens is our 1 and 2 photon states get a little bit closer together. And if you can write this as a Hamiltonian, and if you look at this, you say, aha, we have interactions between our photons. And more or less, these Josephson junctions are the mechanism that we can use to get interactions wherever we want them. For the first part of this talk, though, we're going to really just deal with linear systems and spend a whole lot of time thinking about the interesting underlying lattices we can make the superconducting circuits. And so everything's going to be linear. If you just have one oscillator, it's not that exciting. We can add a second oscillator. Now we have 2 lattice sites. And if we put a capacitor between them, we have a capacitive coupling. This gives us a hopping term in our Hamiltonian, so that if you have 1 photon in one lattice site and 0 in the other, they can hop back and forth. And this gives you this sort of tight binding model for what's going on in these resonators. Now, we're not usually going to be dealing with lumped element resonators. Instead, we make our inductance and capacitive distributed across the chip. So these are transmission line resonators. From a Hamiltonian perspective, they don't look any different. They're still just harmonic oscillators. We tend to make these by essentially taking some long piece of metal, sticking it between two ground planes. This is a coplanar waveguide resonator. So there's a capacitance between the center pin and the ground plane and some inductance along the center pin. And of course, if we want to have two, then we can just have a capacitor at the ends, and photons that sort of live in one cavity can hop in and move over to a neighboring cavity. And this gives us sort of the structure with which we're going to make our lattices. Now, all of this stuff is lithographically defined on a chip, and so we can actually make them to look like almost anything we want, as long as we sort of have them be the right length so that the resonant frequency is in the right spot. So typically they look something like this. So the scale here, this little thing here, is 280 microns. So these are often about a centimeter long. We can introduce meanders in the middle of them, and as long as we don't bend them too sharply, it doesn't really change the frequency. And so we're allowed to really stretch and pull and twist these guys so that the endpoints are very, very close together or very far apart and can move. And that's one of the real superpowers of these resonators. It's going to allow us to build lattices that are difficult to make otherwise. The frequency of the resonator is given entirely by the length. So long as the total length stays the same, they're all the same frequency. And then at the endpoints, if we want to move beyond 1D lattices, we can build three-way capacitors that allow us to couple resonators together into, say, 2D structures like the one you see here. And so each of these meandering lines is one of these microwave resonators. At the endpoints, we bring three resonators together, and this gives us a 2D lattice for photons where they can hop around and move around this lattice. And you can read more about all of this stuff in this review article here. Okay, now, I said this ability to bend the lattices is really one of our superpowers in circuits, right? And so if you think about lattices in atomic systems, the hopping between neighboring lattice sites is really governed by the distance between those lattice sites, right? So if you have two lattice sites, if everything is really equally spaced, then the wave function overlap is well defined and it's constant. If your lattice is incredibly disordered, some things are closer together and some things are further apart. And these, although they're both sort of 2D blobs, actually represent very different Hamiltonians. One has regular hopping and one has hopping that depends on distance. But this ability to bend and manipulate and stretch our lattice sites allows us to make a disordered lattice. It allows us to make a lattice where the centers of each resonator are not equidistant from each other, but the hoppings are still uniform. And the tight binding graph, the Hamiltonian, is really then entirely governed by the connectivity graph and not at all by the spatial distance. And breaking this connection between distance and hopping is what allows us to make really fundamentally strange lattices. Okay, so here, there's one other subtle point that will wind up becoming quite important for our talk, which is that if I sort of draw a picture of where our lattice sites are, and I'll draw them as a straight line just so we don't have to worry about the meanders, you would look at this and say, aha, I've made a 2D grid of hexagons. But you have to remember, whenever I draw one of these lattices, what I'm drawing is actually where the resonators live. But these lines, unlike the way you're used to seeing materials, these lines are actually our lattice sites. And so the resonator lies on the edge of these underlying what we call root graphs. But the actual lattice sites are on these edges. They're the red dots. And you have hopping between two resonators if they share an endpoint. So by drawing these hexagons, what we've actually realized is the Kagame lattice. And this operation of going from the root graph, what we draw, to what the actual hopping graph is called taking a line graph. It's a mathematical operation. And this connection between the root graph and the line graph is going to undergird a lot of what we talk about in terms of making lattices that have interesting flat bands or interesting topological states. Okay, so when we first sort of started thinking about this ability to sort of bend and twist and stretch our resonators, we thought, what's the craziest thing we could make to really drive this point home? And we started thinking about, moving out of Euclidean space. So in Euclidean space, the world is flat. You can tile the world with hexagons, but you could also work in curved space. And in curved space, space is either too big or too small to sort of think about tiling things like pentagons. So on the surface of a sphere, you can tile pentagons just perfectly fine. But in Euclidean 2D space, you can't. You can, if you want, flatten things out and make a picture that does in fact tile pentagons, but the pentagons can't all be equal in size. So you have to break the sort of distance. You can't have the distance preserved. Similarly, in hyperbolic space, you can't squeeze the heptagons in. So if you wanted to tile the space in heptagons, they would overlap. You can do it by making space smaller as you move out, making the heptagon smaller as you move out from these points. But again, you can't preserve distance. But we have the ability now to preserve hopping without preserving distance. And so we can make a circuit map of each of these, where we make our resonators longer as we go out from the center in spherical space, or more sort of twisted and bent as we go away from the center in hyperbolic space. And then even though distance isn't preserved, the hopping T is preserved, and so the graph is preserved. So on a planar chip, we are able to make non-Euclidean lattices. Now, we started doing this because it's fun. There's one thing you have to get used to when we do this is we don't actually have band structure anymore. So in hyperbolic space, translations aren't commutative, so you can't sort of just draw band diagrams. So for the numerics, we just numerically diagonalize some finite lattice and look at where the energies are. And so this is sort of how you would look at the band structure of a Kagame lattice. It has a flat band and then a bunch of states. And if you make the sort of heptagonal, octagonal, or nonagonal Kagame lattice, you can see the bands look here. And if in particular, if you look at the bottom of these bands, you'll note that the heptagonal lattice and the nonagonal Kagame lattice actually have gapped flat bands. Flat bands are exciting because it lets you really look at many body physics with arbitrarily small amounts of interactions. And so we were really interested in these hyperbolic lattices that we can look at these gapped flat bands. And these are flat bands. Flat bands have states that are localized. They don't have momentum, so you can express them as these compact localized states. It's very easy to find them for the even-sided polygons. You just move around one of the even-sided polygons, alternating the sign of the wave function. If you want to do this in an odd-sided space, you can't go around. You can't go around any one polygon alternating the sign because it's not bipartite. So you have to go around two neighboring polygons. And that turns out to be incredibly important. And we'll come back to that later. In any case, we decided we would make one of these. So here is a picture of a heptagonal Kagame lattice. So this is this band structure where we tiled multiple shells of heptagons in order to make a planar representation out of a circuit. This is a few millimeters on about an inch on a side. It's 16 gigahertz resonators. You can measure transmission through the thing, and you can see that there's quite good agreement between theory and experiment in terms of where gaps and peaks and features are. And so we can actually make with pretty low disorder these lattices, again by sort of manipulating the distance as we go very far out from the center. But we are really interested in these gap flat bands because, again, flat bands are really interesting because of the ability to study many body physics, but the flat bands and things like the Kagame lattice, they're not gapped from the other bands. And so the sort of this property that a small amount of interactions will give you many body states breaks down because you'll just mix with the other bands. And so we started thinking about what is it that gives us these flat bands that have gaps, and why do some of our hyperbolic lattices have gaps? And so we started thinking about line graphs. And so, as I said at the beginning, we draw graphene, but we're actually making is the line graph of graphene. Our Kagame lattice, we drew these sort of heptagon graphene, and we got was the line graph of that. You could also think about drawing trees, or in fact, just a square lattice. And when you take the line graph, you get this leaf lattice. If you look at the band structure of these, then you'll see something interesting. And now we're only going to look at the band structure for the Euclidean lattices here, because that's the only ones where we can actually compute a band structure. But if you look at the band structure for a square lattice, you get these beautiful looking bands. And if you look at the band structure of the line lattice, you'll notice that the band structure is exactly the same, except instead of going from -4 to 4, it goes from -2 to 6. So it's shifted up in energy, and this orange flat band appears at -2. If you look at graphene, you get these two bands. And if you look at the Kagame lattice, which is the line graph of graphene, again, it's shifted up so that the bottom of the bands are at -2 and a flat band appears at -2. The question is, why is this happening? And can we use this to figure out how to make gapped flat bands? So we have a math paper on this in Communications and Mathematical Physics. So you can start with a Hamiltonian of your sort of root graph. This is the thing we actually draw. And you can think about the Hamiltonian of the line graph. That's the thing that we actually realize. And you can relate the root graph and the line graph with this incidence operator. So this is an operator that takes the root graph x to the line graph L of x. And you can think of this as a matrix that has edges on one side and vertices on the other. And if E and V are incident, then you get a 1, and otherwise you get a 0. So this is an operator that you can multiply by a vertex and get the incident edges. And if you look at what happens to a vertex under operations of this, you can figure out why we get this correspondence between the eigenvalues of the line graph and the eigenvalues of the root graph. So if I start with a vertex here and I multiply by my incidence operator, then I get the 3 lines, the 3 edges that are incident to that vertex. And now if I multiply that by m dagger, then I get back to my original vertex 3 times, once from each of these edges. Plus I get these 3 vertices that were the neighbors of my original vertex. And this is in fact the hopping operation. This is the Hamiltonian operating on this original vertex, because you hop to all of the neighbors. And so this can be described as my original Hamiltonian plus a diagonal matrix with the degree. So in this case, it's a degree 3 regular graph. We can do the same thing starting with an edge. So if we start with an edge and we apply m dagger, we get the 2 vertices that are incident to that edge. And then if we apply m on top of that, we get all of the edges that were adjacent to my original edge, plus I get back to my original edge twice. So this is 2 times the identity matrix plus the Hamiltonian of the line graph. And it's the correspondence between these 2 things that allows us to make this energy correspondence. In particular, any eigenvalue of m dagger n, or any eigenvector of m dagger n, has a corresponding eigenvector of m dagger. And in fact, it is just m times that eigenstate. And the eigenvalue of both of those are the same. So for any eigenvalue of this operator, which is also has to be an eigenstate of the Hamiltonian, we can find a corresponding state in this of this Hamiltonian with the exact same eigenvalue of the m's. And so if the eigenvalues of these 2 things are equal, and you kind of bastardize notation a little bit, you can find the energy of everything in the line graph is just my original graph shifted up by d minus 2. And anything that's not my original graph has to be in the kernel, and it just winds up being flat and at energy minus 2. And so this allows us to sort of think about all of these graphs, and the energy of any of these graphs is the energy of the root graph shifted upward with a flat band at minus 2. And you can sort of see it from these density of state plots. And if you want your flat band to be gapped, what it says is that you need the minimum eigenvalue of the root graph to not reach the minimum possible eigenvalue. So a regular root graph of degree d has all of its energies between minus d and d. And if the graph is bipartite, you can always get an energy state that is at minus d just by coloring every other vertex a different color, and then keeping an equal superposition of all of these, alternating the sign positive to negative. That will always have energy minus d. And when you take the line graph, that will always have energy at minus 2. So every bipartite graph will have the line graph of a bipartite graph will always have a flat band, but it will never be gapped. But if you have a non-bipartite graph, you can't make this, this coloring in terms of the sign, and then you actually always get a graph. And so the simplest graph we could make doing this was to essentially tile heptagons and pentagons. It's to essentially add these interstitials to the graphene lattice. You can think of this, if you want, as being locally curved between positive and negative, sort of rows of pentagons and rows of heptagons. And if you calculate the band structure, you will indeed see that you wind up, along different directions, you wind up getting a flat band at -2 that is quite heavily gapped. And in this paper, we talk about other ways of getting these gap flat bands. And in particular, we also talk about how to optimize how large the gap is. But we now have a prescription for how we can draw a root graph. If it's a non-bipartite, if the line graph will always have a flat band. And if it's non-bipartite, we will always get a gap flat band. And so now we can use our circuits to build really new classes of lattices that all have gap flat bands, which is a great sort of starting point for beginning to think about many-body physics in these systems. Are there any questions? Because we are at break number 1.
All right. Thank you very much, Andrew. Indeed, we do have a number of questions. So we have one family of questions, which is sort of about topology of the physical systems. So one of the questions is, does being on a single plane of a chip place any constraints on the geometry you can realize or the connectivities? Relatedly, what if you need more than 3-way connectivity? And finally, are there hopes for using 3D superconducting circuits? So
yeah, great question. So the first one, if we're only on a single plane of a chip, we can only realize planar graphs, so we can't have any edges of our graph cross over each other. That's not a fundamental restriction. People are starting to make graphs that have 3D connectivity, but right now we're only dealing with planar graphs. There's some guys at Chicago who are doing some cool graphs with 3D cavities. I forget their names. So Dave and John have been doing really great work with 3D cavities. Generally, they've been dealing with more standard lattices, but doing interesting things like putting Yig crystals in to break time reversal symmetry. But for some of these lattices, there are ways that you could begin to do it in 3D cavities as well. In terms of couplers coming together, the 3-way coupler is the easiest because it's in some sense fundamentally disorder free. You can make all of the hoppings the same by symmetry, but there are Christy Chu in my group, who's been working on this stuff, has been developing all kinds of new shaped resonators and can do 6-way couplers and n-way couplers, all kinds of things now. And so the building blocks are getting built to make all kinds of crazy lattices.
Cool. Okay. Another question. In the transmission curve, the theory curves seem to be made up of many curves. What distinguishes the different curves?
Right. So there, we wanted to sort of get a sense of, what small amounts of disorder. So we assumed that there was like a part in 10 to the 4 disorder, and came up with a set of theory curves where we just sort of re-diagonalize over different instantiations of disorder in order to sort of understand like what kinds of, put a bound on how much disorder we saw.
Okay, so we have a whole bunch of additional questions. I'd just like to ask one more, which is, you made this comment about heptagons and pentagons giving you an isolated flat band. But that corresponds to a combination of positive and negative curvature, right? Alternating. So I guess the question is, should I then think that it's impossible in a physical lattice that lives in a plane to get an isolated flat band?
Well, okay. So it is not impossible in a physical lattice, and these are all Euclidean lattices, right? So I guess my point was, if you tried to force these lattices to have equidistant atoms, you would have to break the plane, and I think it would result in a ripple in the plane. But it's fundamentally a Euclidean system. So you could also just have them in a plane and carefully tune your tunnel barriers and not have everything actually be equidistant.
I guess what I was sort of asking is, are there examples? I don't know of examples of flat bands in planar crystals. isolated flat bands? And is this maybe part of why?
It's a good question. I know Under Bernawig's group has been doing something where they've been using some of this sort of flat band technique to actually comb through databases of 2D crystals and looking for naturally occurring flat bands. And none of them are perfectly flat, because real materials are, you know, messy and real. But they can find things that look like elements of line graphs or certain kinds of line graphs, right? The Kagame, you know, is a line graph, but it's not gapped. But you can induce gapping in real materials from like spin orbit coupling and other things like that. So, you know, it gets messier in real materials.
Okay, so there are a whole bunch more questions, but I think this is a good place to leave it, and let's push ahead. So thank you, Andrew.
Okay, and I'll be hanging out at the after party too. So, you know, you can ask more things there. Okay, so you know, we have these flat bands, and so the question that Christy has really been asking in the group is now, what can we do with them? And one thing that you can do with them is you can add in interactions, and that's something that is definitely ongoing in the group. But another question you can ask is, you know, are any of these things topological? Are they actually topologically interesting? Because there are a number of things in life that are flat bands that have sort of interesting topology. And so here's a question, which is, how can we tell if any of these flat bands actually have interesting topological properties? So just to remind you where we were before we took that break, we had flat bands, we had flat bands that came from taking a line graph. And now what I want to ask is, what is the degeneracy of that flat band? How many actual bands are there at -2? And you can find this by a counting argument. So if we take our original root graph, if there are some number of sites per unit cell, then that tells you how many bands there are. So for instance, in the graphene example, there are 2 sites per unit cell, so there's 2 bands total. If you look at the line graph, it's a degree 3 object. If you look at the line graph, there are ND over 2 sites per unit cell, because the number of edges in the root graph is ND over 2. So there's ND over 2 total bands. But we already know what 2 of the bands are. We know what N of the bands are, because N of them are just the displaced versions of our original bands. And so the degeneracy of the flat band is everything that's remaining. So it's ND over 2, the number of bands in the line graph, minus N, the number of bands in the root graph. And so we can compute the degeneracy of that flat band. And once we know the degeneracy of the flat band, we can start to probe whether these are topological. And we're only going to really concern ourselves with cases where the root graph is non-bipartite. So to answer this question of whether something is topological, we're going to be delving into this world of topological quantum chemistry, and so we're gonna sort of go through a construction of how to figure out if something is topological. By the way, this is going to be again very theory-ish, but I really am an experimentalist. I'm not lying. So topological quantum chemistry, says that you can you can use it to generate all of the lattices which have a Wannier representation, and you can determine their bend representation. And so you can really figure out if your lattice is topological or not. So the idea is you start from a symmetry group. For each symmetry group, there's a bunch of maximum Vygotsky positions. These are the points of high symmetry, and these all come with some unique identifier which has a number which tells you the multiplicity, and a letter which tells you where it is that you're talking about. So these like non-shaded out triangles are the 2B sites in this lattice. And then you also have to pick an orbital type. Is it an S orbital? Is it a P orbital? At any given lattice site, we're only dealing with S orbitals in this talk. But if you're taking the set of flat bands by themselves and you're only considering those flat bands, then your orbitals are actually these compact localized states that live in those flat bands, which actually consist of weight on many different lattice sites. And you can think of those as S orbital-like or P orbital-like, depending on their symmetries. From these things, from the symmetry group, the orbital location and the orbital type, you can come up with what's called an elementary band representation, which tells you, the type of orbital and the orbital location. And when you turn these into a band, that's what the G means, then this band representation tells you fundamentally what the properties of the band have to be. So A to B has 2 bands that have 1 touch at the K point, and that has to be the case. And so you can abstract away everything about the energies. You don't know the energies, but you can learn about the shapes of the bands. For instance, if you had p orbitals, pz orbitals, and spin, then you would write this as E2b. You would get 4 bands that had a touch at k and 2 at gamma and 2 at m. And in fact, there's multiple ways you can get this, but it tells you something about the structure of the bands. Now, this can tell us something about topology, because we can think about topology by thinking about, say, what happens if you had a Fermi level. So anything that has an elementary band representation isn't topological, and anything which can't be written as an EBR or a sum of EBRs has to be topological. So if, for instance, if we had a Fermi level that was sitting right between these pairs of bands where there's a gap, then you would essentially have electrons only in the bottom 2 bands and not in the top 2 bands. And the structure of this object is then fundamentally topological, because you don't have a full EBR, you only have a part of an EBR. And we call this stable topology because you can't represent this as a sum of EBRs by adding more sort of trivial bands, by adding more EBRs. You have to add the top 2 bands here, which are, you know, the other half of that EBR. And so this is stable topology. Now, if we want to sort of figure out whether our lattices have topology, we basically then need to figure out, is it a sum of elementary band representations or not? And that means we actually need to determine what the elementary band representations are. And so Christie's paper goes through this in beautiful detail with really pretty figures. But I hope to give you at least a flavor of what's going on, Matt, going through this line graph of the triangular lattice as an example. And so first, we're going to restrict ourselves to the states that are within the bands we care about. In this case, this is a non-bipartite line graph of a non-bipartite lattice. And so that means we have a flat band at -2. And we're going to restrict ourselves to those bands, its gaps, so we can cut away everything else. And so to do that, we actually need to know what the compact localized states are. And so we can go and look at what the compact localized states are. We can look at what the compact localized states are. Okay, go. And so to do that, we know how to find these, right? And the idea is you go around some closed loop, alternating sign of your wave function. And what happens at that, if you're in a line graph, if you have 2 things that have opposite sign, you can't hop off of that point because you get a destructive interference of the hopping from those things. And any latticite is sort of, when you apply your Hamiltonian, gets hopped onto from 2 adjacent laticites, and that gives you the eigenvalue -2. And you also have some extended states. So we can sort of figure out how to draw these compact localized states. And once you know those, then you can determine the elementary band representation. So for instance, the compact localized states of the triangle lattice are these rectangles or bow ties, depending on how you like to think about them. And the next thing you need to do is work at each Wyckoff position. You find first what the symmetry is around that maximum Wyckoff position. So here we're going to take the 1A position, which is this thing in the red circle here. It is C6 symmetric. So there's a 6-fold rotational symmetry around that. And we want to construct the eigenvalues and note the number of eigenstates with each eigenvalue around this particular Wyckoff point. And we do that by knowing that the eigenvalues have to be multiples of e to the I2 pi over 6. And we can construct these eigenstates by rotating our compact localized state 6 times around that point and adding a phase here, which is e to the I k2 pi over 6 each time we do a rotation. And when you do that, you get an eigenstate of the symmetry group, the eigenstate of C6, but you only get it if you don't actually annihilate everything when you add this state together. So for instance, if you think about k equals 0, we're going to add this state here. If we rotate it once and add it, you get a positive thing on top of a negative thing. And if you just keep doing that, you always have exactly 1 positive and 1 negative. Everything adds to 0. And so there isn't actually an eigenstate for k equals 0, but there are eigenstates for k equals 1, 2, and 3. This gives you what we call the real space invariance, which are these deltas. And this tells you the difference between the number of eigenstates with a k equals 1, 2, or 3, and the eigenstate k equals 0. And it's 1 for each of these rotations. And these are the real space invariants. And no matter what bands you choose, or what states you choose to represent your bands, these invariants are always, always, always true. We do this for each Wyckoff position. So at the 2b Wyckoff position, which is here, when you rotate things, you don't actually get any destructive interference and nothing annihilates. And so there's an equal number of k equals 1 eigenstates and k equals 0 eigenstates. And for the 3c point, it's C2 symmetric. And if you do the rotation around this and add it together, you actually get a k equals 0 eigenstate, but you don't have a k equals 1 in eigenstate. That sums to 0. And so you only have a -1 for this elementary, for this real space invariance. Once you have your real space invariance, you have to compute the band representation. And that basically means just solving a system of equations. So at each Wyckoff position, we know how many times that Wyckoff position appears. So it's either 1, 2, or 3 for the multiplicity 1, 2, and 3. And then from the real space invariance, we know the differences between the number of bands at different k values, and those have to be fixed. And if you count the total number of bands, it has to equal the degeneracy of the flat band. So, for each Wyckoff position, you can count some bands and you add it all up, and you get an equation which is constrained by the total degeneracy of the flat band. And when you solve it, you actually find the sort of unique number of each kinds of bands that have to exist. And sometimes when you solve it, you will find that there's the only possible solution has a negative value for some particular band. Because remember, we're not dealing with the entire structure, we're dealing with a restricted number of bands. And so the elementary band representation of this is 3 s orbitals at this 3c Wyckoff position and -1 s orbital at the 1a position. And that's the only way to represent the bands here. Now, this is not a sum of elementary band representations. It's in fact a difference of elementary band representations. So if you contain only part of an elementary band representation in the space you're considering, that's what we call stable topology. And if it has only a fraction of an EBR, it can't be destroyed even by adding any sort of trivial bands. If it is a difference of EBRs, it still isn't a sum of EBRs. So it has to have a von Neumann absorption. So this has to be something that has something that's topologically non-trivial. But this is called fragile topology because it can be destroyed by adding sort of an ordinary, boring, elementary band representation. And in particular, if we add one more A1A band, then this is no longer a difference of bands. Then it's just three things here. And so this elementary band representation tells us that this is topologically interesting, but in a way that is fragile, and that's what we mean by fragile topology. And if you look at the Wilson loop winding, you can see that there's actual winding, so it is in fact topologically interesting. And so this gives us a procedure for building lattices out of our line graphs that are in fact topologically interesting. And this tells us the kinds of things we want to build. So the idea, the idea is, okay, so one thing you note is it might have something to do with faces, because you can use this identity about the number of faces being the difference between the number of edges and vertices and show that that's the same as the degeneracy. And so the idea is you could, for instance, just generate all the possible line graph lattices and do this sort of exhaustively, right? So if you want to look at things that are degree 1, there's only a finite number of solutions to having ND minus 2 equal to 2. So this is the equation you get here if you want degeneracy 1. And those are n equals 1, d equals 4, n equals 2, d equals 3. And none of them are non-bipartite, so nothing is gapped, and so there's no degree equals 1 lattices. For degree equals 2, there's 3 possible solutions, one of which is the triangle and one of which is this nonagon triangle. This first one is actually topologically interesting. And so you could just do this for every lattice. But more interestingly, we've been working on trying to prove rules that are based on symmetries in order to figure out how to construct topologically interesting lattices to start from. So the idea is you start from your root graph. So you start from geometric properties of your root graph, which is really just how many even and odd-sided faces does it have. From that, you can tell where the Vyckoff positions lie within each unit cell. Do they lie on a face, or do they lie on an edge, or do some of them lie on a face, or do some of them lie on an edge? And the underlying symmetry of the lattice and the sort of underlying properties of the root graph tell you where they have to lie. Once you know where they have to lie, you can figure out this is in the root graph. You can then figure out what happens at a line in the actual line graph. So a Wyckoff position on the face of a line graph, a face of a root graph, also has a Wyckoff position on the face of a line graph. A point on a root graph an edge of a root graph becomes a vertex on a line graph, and a vertex on a root graph becomes a little complete subgraph on a line graph. From that, you can actually figure out what the real space invariants are. So the faces, vertices, and subgraphs tell you, in fact, exactly what the real straight invariants are always. And remember, this is what we use to solve that system of equations. You can then solve that system of equations for each of the Vyckoff positions, and you can figure out, the topology. And so for this, you can figure out that for d equals 1, there's no gap bands. There is a flat band for d, a topological flat band for d equals 2. There are none for d equals 3 or d equals 4. But remember, you can destroy fragile topology by having extra non-trivial bands. So it could be that something in one of these states is non-trivial, but in order to see that, we have to split off one of these bands. And so we actually add a perturbation to reduce the flat band degeneracy. And all we really have to do is add a perturbation that preserves the original symmetry. You can't actually do that for d equals 3 graphs. But for d equals 4 graphs, we can do that. And once you do that by, for instance, adding one extra, so here's the topologically trivial band, you can add one extra sort of set of hoppings, and then you actually wind up getting winding again. And you can see that it's a difference of EBRs. And so we have a procedure that allows us to construct kind of arbitrary lattices that we can build, and not just one, but whole families of them. And we understand the symmetry properties that allow us to sort of build them up and make topologically interesting sites. These are much more complicated lattices, but they're all things that we can actually go ahead and build. So, you need a 6-way coupler. Well, we've built that. You can have sort of T and X or Y and X-shaped resonators. And those are things we've now built with or sort of designed with known frequencies. And then we have ideas on how to actually measure fragile topology. And then, of course, if we want, we can add qubits to turn on some interactions. So we have all the ingredients to really do sort of gap flat bands that are topologically interesting with or without interactions. And that's where the experiments are heading right now. And that's pause number 2.
All right, great. So we have a couple of questions here. One is, are there nice experimental observables for probing this sort of topology? Put another way, what sorts of physical changes, like local disorder maybe, make this topology fragile versus a strong topology?
Yeah, so I think it is not that it's necessarily fragile. It's fragile. It's still topological. And so you still have these extended states. It's fragile in the sense that sort of adding additional bands or band mixing can really destroy the topology. So you do have to make sure that you don't have enough disorder that you mix in something from some other bands. But there are spectral signatures that you can look at, and so we're trying to think about how you calculate things, sort of looking at these sort of twisted boundary conditions. But yeah, it's a really good question about sort of what boundary properties we actually are going to be able to measure to show that we have these topological sets, but we're starting to probe them. Okay,
so a couple more questions. One is, and this is actually my question. I think I may have asked this a while back. Is there a possibility of, hey, I'm the MC, so I get to ask my questions. If you don't like it, you have to be the MC. And this, incidentally, is why they don't let me MC very often. Is there a possibility of adding flux to some of the couplings, and is there a sense in which that affects the story?
So yeah, it's a good question. I don't understand. I don't actually know, right? In some sense, there's different ways that you can get topologically interesting things, right? You can have these, time varying fluxes that you use to do interesting things across the lattice. You can have your Yig crystals, which fundamentally break time reversal symmetry, and you can get these things that are, in some sense surprising because there's no broken time reversal symmetry, right? These don't have non-trivial churn. These don't have non-trivial churn numbers, but they still have sort of this interesting sort of fundamental topological property. And so it's, I don't know if you add flux to something, and start to try and break time reversal symmetry or something on something that is topological in this sense, then you might I don't get a sense that if you created something that had stable topology and I don't know that would be interesting. In some sense, the interesting thing is that you don't need flux. But I'm not positive about that, right? I'm still learning about all the things that could potentially be interesting here.
So I think another pretty nice question to ask, which follows up on these, is does topologically non-trivial here have the same consequences as it does in condensed matter physics? E.g., are there robust edge states residing within the gaps?
That is a good question. I believe yes. Right, you definitely have these extended states, right? Right, that's what it means that you don't have a Wannier representation. So you can't have everything just be defined by these sort of exponentially localized states, and so that seems like would have to mean that you have these sort of extended states.
Okay, we do actually have even more really fun questions that we can't ask because I asked my stupid question. So I think now we should let you tell the last piece of your story. So I apologize to the other question askers. You can ask at the end or in the after party. So
okay, so I'm gonna conclude by showing some actual experiment that we've been doing. Not on these crazy lattices, but on super simple lattices, but with crazy interactions. And so this is work that Andre Rajacharya has been pioneering in our group, and he's now Dave Schuster and John Simon's postdoc. So he's continuing to do cool latticey things. So this is sort of based on these sort of 1D photonic crystals that Jeff Kimball sort of proposed for real optical sort of photons and looking at photonic bound states. Here we create a 1D photonic crystal either by modulating the impedance of our waveguide or by just making a 1D array of cavities. And when you do this and you put a single qubit in as a scattering element, then you can see that you actually get photonic bound states around that atom, and so you get sort of really interesting sort of light matter interactions. If you have two qubits, then you wind up getting two photonic bound states, and you can get interactions between the photonic bound states. But here I want to sort of see, this sort of question of what happens if we start to get a very, very strongly coupled single defect. And look at sort of how it couples into the open continuum. And I really want to sort of add this after those topological and flat bands, because those become really interesting as we start to add different kinds of elements that promote interactions. And I want to show sort of the range of the kinds and strength of interactions that we can get in these systems. People have been thinking about different ways of pushing the sort of limits of light matter coupling, whether you get sort of the coupling between a single atom and a photon, which is really the coupling between two photons to be on the order of the frequency. In a multi-mode cavity, you can get it to be on the order of a free spectral range and get mixing between the modes. And then in waveguide QED, you can get it sort of the coupling, the openness on the order of the frequency, so the decay rate on the order of frequency, and you can see some really sort of interesting physics there. Here, we're going to be looking at sort of very, very open quantum systems, but also ultra strongly coupled quantum systems. So it's a qubit embedded in an array of cavities. You can think of this in the eigenmode basis as some array of modes and some coupling, and the modes sort of follow some particular 1D band structure. But our coupling is going to be strong enough that the rotating wave approximation breaks down, and we really sort of build up this incredibly interesting scattering between the collisions of these photons. The way we do that is by using not a transmon qubit, but a fluxodium qubit, which is basically just a large flux loop or an inductively shunted Josephson junction. And the trick that we do is we have some of the inductance of the qubit shared with the actual center pin of the cavity, and that allows us to get incredibly high coupling. So here you see a picture of the 1D array of cavities. So here there's 26 cavities in a 1D chain that we sort of meander about, and in one of them we put this this qubit, which gives us this very ultra strong coupling element. And in the part of the inductor that's shared with the cavity, we actually put a series of small loops. And this allows us to effectively tune the inductance, and this allows us to effectively tune the coupling. So if we change the magnetic field through this whole thing, very quickly we'll be changing the frequency of the qubit, but more slowly we'll be changing this mutual inductance, which means very slowly we'll be changing this relative coupling strength G. And so we can see the onset of non-rotating behavior. And so when you tune this frequency, it looks like this. So here, this beautiful, beautiful like sunset on ripply water. Each of these ripples is when the qubit comes into and out of the passband. So this colored area is sort of the band of the cavities. This is the band structure of the cavities. And as the qubit comes in and out, you see these sort of bound states forming. But with each successive ripple, the coupling gets stronger and stronger. And so for the first ripple, you can sort of look at this and you can actually fit the general shape of this in this black cut to look at how open we are. And actually the openness of our qubit to the waveguide is something like 0.7 times the frequency. And so we're really open environment. But now as we increase G, you can start to see that we get some multi-photon scattering processes. And so you see the structure starts to develop, and you can see now this 2-photon and now even a 3-photon bound state. And in fact, if you sort of look at a model of the system as you turn up the coupling, you first see this mode from the qubit pushing into the passband. But if you make the coupling stronger, the 2-excitation manifold comes down into the passband, and then the 3-excitation manifold comes into the passband, and you start to see these multi-photon bound states, which sort of show that your scattering is a multi-photon complex process. You can also look at inelastic scattering in these devices. You can sort of pump at the lowest frequency and look at what comes out. By measuring the sort of power that comes out at every other possible mode of the system or at every possible frequency of the system. And you can see that there's actually a really interesting inelastic scattering profile that happens. If you pump at the bottom, you inelastically scatter photons all throughout the band, not just at the cavity frequencies, but actually also in between. You get this very, very interestingly structured sort of inelastic scattering. As you increase the power of your pump, at some point it very suddenly jumps to this scattering where you actually get inelastic emission exactly at the underlying modes of your lattice. And that sort of sharp transition happens when you sort of push the bound state out of this passband. Now, what we suspected was that this process is not just sort of scattering to other modes, but it actually is creating this massive multi-mode entanglement. And that's something that we can also measure in these systems. So we can measure sort of correlations between the different modes coming out of the cavity. And in particular, we look at this Hilary's Very criteria to try and see, do we actually have entanglement between our modes? And so violation sort of implies that we actually do have entanglement. So to do this, we look at our inelastic scattering, we split it into multiple channels at a beam splitter. We then measure both in-phase and quadricular components. And then we have to do a little bit of processing, right? So these are microwave photons. They're not as easy to detect as optical photons, but we can subtract off all of the sort of noise elements and come up with this sort of criteria. And we can plot this as a function of the pump power. And what you see is that as we pump the system, it goes from something that is entangled to something that doesn't look so entangled. So here, these color plots are actually plotting the entanglement pairwise between each of the 25 modes of the system, and anything that is sort of red shows that there's entanglement, and anything that's blue is sort of below the threshold for a violation. So it doesn't really tell us anything. And so you can see that as we increase the pump amplitude, at low pump amplitudes, this inelastic scattering really is giving us this massive multi-mode entanglement. And then we can look at this entanglement criteria as we approach this point where everything in the emission changes, and right at that point we actually plummet in this sort of entanglement criteria. And so you can see that we actually can trap out this multi-mode entanglement. And all of that is just to say that we have these sort of really interesting lattices that we can build, but we also have the ability to turn on these really interesting interactions and and look at the interplay with the openness of the quantum system, and it really gives us this nice playground to work on. So I just want to acknowledge in my last few minutes the people who did the actual work. So for everything on the hyperbolic lattices and the gap flat bands, that was my former postdoc Alicia Kolar, who's now starting up or well into starting up a research group at JQI at Maryland, and is always looking for really great students, and she's fantastic. So you should go work for her if you like that stuff. Matthias Fitzpatrick was the lead student, and on the math stuff we worked with Peter Sarnak in the math department. For the fragile topology, all of that work was really led by Christy Chu in my group, working with folks in Andre Berdovic's group. Christy was a former Marcus Greiner student and Daymont Prize winner, and now superstar postdoc in my group, probably going on the job market this fall. You should hire her, just FYI. And then Andre Rajakarya led the ultra strong light matter interaction experiments with theory support from Alexei Gorshkov group. Andre will be on the job market soon enough. He's doing his postdoc with Dave and John, but also doing really absolutely fantastic stuff. So just to include, here's all the things I talked about today. I'm happy to answer questions on any of them, and hopefully I've convinced you that superconducting circuits are cool.
Thank you very much. So we have a whole bunch of questions. I think the most pressing one is you kind of say a boot. Are you Canadian?
Everybody says they think I'm Canadian. I am like born in Maryland and raised in New Jersey, and I think it's just some weird cross-pollination of like Baltimore and New Jersey accents that makes me sound.
That person
like
came
Canadian.
from Christie, just so you know. Okay. Not just kidding. It didn't come from Christie. Okay. So we have the question, can you benefit from being able to measure the excitations in individual resonators, or from adding more outcouplers, or is all of the information in the spectrum? I think this is referring back to the previous section of the talk.
Yeah. So I think the more places you can measure, the happier you are. So sort of very early on in my talk, I actually showed this faux what is like our version of the quantum gas microscope, except for like photons. So this thing at the bottom left here is actually a scanned probe measurement that we can use to actually read out what's going on at every possible resonator in the system. So we do have that capability. It's kind of actually a little bit annoying to do, but it's a thing that we can do. I saw a recent experiment on the archive, and I don't remember who it was, who actually used a laser to like locally warm up resonators, and that's another way you can actually look at imaging or do defects. And I'm sorry to whoever's work it was really nice, and I can't remember who. So there are ways that you can do sort of imaging across the 2D plane. You'd be much happier reading out more things, but you can learn a lot from the transmission of the spectrum. One thing that we've started to think about is also doing point-wise correlations, right? So if you have a relatively small number of outputs, you can look at correlations between different lattice sites. And I think that's sort of the trade-off that you have in these systems, right? So you can build smallish systems with absolutely almost no disorder whatsoever, right? You can sort of do what like Dave and John did with the mod insulator experiment and really tune everything up to be perfectly on order and measure every property of your system, or you can build bigger and bigger systems where you have a little bit more disorder, or you can't measure every latticite, or you can't measure every property of every latticite, you have to sort of have this trade-off in computational complexity. If you really wanted, like IBM has a processor and Google have processors where you can read out every possible latticite, but they're in sort of normal standard lattice configurations. And so, these are more like application specific quantum computers, right? They simulate interesting challenges, and then you have to make a little bit of trade-offs. But you can learn a lot from the spectra, you can learn a lot from correlations. And in some of our experiments that are online, we have some experiments in relatively small versions of these interesting lattices where we hope we'll have control over actually every latticite and be able to measure every latticite.
Thank you. Okay. A couple more. In the last series of slides, what are roughly the line width decay times for the coupled resonator systems? So from lots of loss to the environment with the extra couplers.
Right. So in this last set of work, we actually wanted sorry, which last this photonic crystal.
Yeah,
this photonic crystal, we actually wanted things to be super open to the environment, right? Sort of what was interesting, in some sense, is that we're sort of repeatedly scattering photons at a pretty high rate, and it's this openness that really helps us, couple all of the system, everything together, and give us something that really looks more like a band and less like a bunch of individual resonators. And so it's this sort of interplay between ultra strong coupling and the openness to the environment that gives us this sort of really interesting scattering physics.
Okay, thank you. Okay, two more questions, and then I think we should wrap. Actually, you know what? We'll just do one more and then wrap up. So how much control do you have over the resonance frequencies of the individual resonators and the couplings between them? Is it possible to make it entirely homogeneous? Do the imperfections result in detuning disorder?
Yeah, it's a great question. So disorder is always the bane of people who make circuits existence, but in terms of the linear resonators, it's not actually so bad. So in our earliest paper on making the Kagame lattice, we found something like a part in 10 to the 4 disorder over our resonators, and the couplings are also pretty easy to control. And so if you're just making a linear resonator, it's not that hard to get it to be low disorder, especially when the disorder has to just be small compared to, say, the hopping rate or the gap between your flat and your unflat bands. The challenge in disorder starts to come in when you start to add qubits. So we've done sort of an experiment where we had a 1D array of resonators, each which had a qubit that had strong interactions, but there the qubits were very disordered, and that leads to it being an experiment of the physics in a disordered array, which itself I thought was actually quite interesting. But if you want to have low disorder in your interactions, you need to be able to tune up your qubits, right? And so in Dave and John's experiment on the mod insulator, they tune up each individual qubit, but then they have only a relatively small chain of qubits, because tuning up too many things gets to be problematic, or at least annoying for the poor graduate students.
Problematic for me. I just said it.
But now there are ways around that. So IBM has sort of recently written a paper on how you can do a room temperature pre-measurement of the resistance of each of the junctions, and then sort of use a laser to in situ tune them to be right. And they've shown that they can get the disorder in the qubit frequency down by, I think it's like a factor of 80 or something over what it naturally is. And if you do that, then you can actually start to make large systems with fixed frequency transmons with low enough disorder that you can really look at these flat bands with interactions in each. And so there are paths forward that don't involve large amounts of tuning things up. And as this field gets better and better at these scaled systems, we get less scared of like bigger systems. Like I think Christie could do like 20 without a problem, right? But in the
is that a statement? Is that a statement about Christie?
It's
Dave, how many could he do? Okay.
What's that?
I think, let me just say, I think we should thank Andrew again for really engaging and wonderful talk. We have two more orders of business here. The first one, Andrew, I'm going to have to stop you from sharing your screen for a second. So I'm supposed to show what's next, but I really felt like it was important when I searched for Andrew's CV. This came up from, I think, probably 2002 or something. So this is Andrew at MIT. His website from the Media Lab is still there. So anyway, these are the upcoming talks, both for our sister series. Didi Liebfried is giving the quantum science seminar, and in Vamos next week, Gerhard Rempe will give the talk. And the last order of business here is the after party, where those of you who didn't get your questions answered can ask them of Andrew. So I guess that should be posted in the chat. And we will see all of you over there. So thanks again, Andrew. But just so we're clear, you're still